Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today, we're going to talk about an example of simple harmonic motion. Experiment 1. A block of mass 0.3 kilogram is placed on a frictionless table and is attached to one end of a horizontal spring of spring constant K as shown. The other end of the spring is attached to a fixed wall. The block is set into oscillatory motion by stretching the spring and releasing the block from rest at time t equals to 0. A motion detector is used to record position of the block as it oscillates. The resulting graph of the velocity v versus time is shown. The positive direction for all quantities is to the right. So determine the equation for Vt, including numerical values of all constants. So here is the motion diagram, and here is the actual lab setup. You know when you release this block, the block is going to the left. That means the velocity has to be negative. And as you can see, this is a sine function. This, as a matter of fact, is a negative sine function. So your v should be negative a sine omega t. What is A? A is the amplitude. In this case, A is the V maximum, which is 0.16. And that's the maximum velocity. Omega is called angular frequency. And from angular frequency, from this diagram, we know the period. Period is time for one cycle. So in this diagram, it tells us period is 0.7 seconds. Omega is 2 pi over t. That's a relationship between angular frequency and period. We know period is 0.7, so we can figure out omega is 9 radians per second. Plug everything in, A and omega, you'll have the equation as a function of t. Part B. Give that equilibrium position is at x equals to 0, determine the equation for xt, including numerical values for all constants. So again, to find displacement from velocity, you'll have to do integral. We know velocity is this, x is just integral of velocity. We also know from here, your initial position, x really is at your amplitude, the maximum position, right? And so this A over omega is your maximum position. What is omega equals to? We already know omega is 9 and A equals to 0.16. Plug everything in, you should have x equals to 0.018 cosine 9t. So that makes sense. When t equals to 0, x equals to 0.018. That's a positive maximum displacement. Then the block is going to move in the negative direction past equilibrium and vibrate back and forth. Next one, you have to calculate the value of k. That's a spring constant. How is spring constant related to mass and period? Here is the equation. Period equals to 2 pi square root m over k. You can square both sides to find k. So t squared equals 4 pi squared m over k, and switch t and k. So you have k equals to 4 pi squared m over t squared. You know what t is, you know what m is, simply substitute in. You should have kilograms over second squared according to our substitution with units. This is equivalent to newtons per meter. Experiment 2. The block and the spring arrangement is now placed on a rough surface. On a rough surface, that means energy is not conserved. The mechanical energy is changing to heat. The block is displaced so that the springs compress the distance d and release from rest. So in this case, your block, when you release it, velocity will become positive. Okay, so the first question is on the dot below that represents the block. Draw unlabeled forces, not components. That's x on the block when the spring is compressed the distance d, x equals to d over 2. So somewhere in the middle over here, while the blocks in this case is moving toward the equilibrium position. That means block is moving to the right. So over here is equilibrium. When the position is less than equilibrium, force is always pointing toward the equilibrium position. So in that case, the force from the spring is to the right. But because block is moving to the right, force of friction would be to the left. The other two forces are gravity and normal force. So these are the free body diagrams. When the block is moving away from equilibrium position, that means it's going to the left. Again, it doesn't matter which way the block is moving. The force from the spring always pointing toward the equilibrium position. So force from the spring always in this case, pointing to the right. But friction in this case is also pointing to the right. That is because the block is moving to the left. So both friction force and the force from the spring are going to the right. The other two forces stays the same. Normal force always up, gravity is always down. Lastly, you have draw a sketch of V versus T in this case. So assume there is negligible change in period and the positive direction is still to the right. So V is supposed to go positive. So instead of like last diagram, V goes negative, this time V is supposed to go to positive. One thing important is the period is the same as before. So that's first you do the period points. That's still 0.7. Those are the periods. So, and the points between the periods, I would graph also because those are your 0 points. That's half of the period. Between the half period is your maximum amplitude. So because the velocity is moving positive, so you have a positive first, then negative, a positive, negative, and positive, and so forth. As you can see, because you have a friction, so the amplitude should decrease to indicating total energy has decreased. So this is how you do it. Okay, that's it. Thanks for watching. See you next time.